Welcome, this is a recorded session of the Post-Quantum Cryptography Conference of the PKI Consortium. This conference would not have been possible without our sponsors, PQ Shield, SSL.com, Entrust, Keyfactor, HID Global, and the organizational support of the Post-Quantum Cryptography Working Group of the PKI Consortium, and in particular, Entrust, Keyfactor, and Logius. Would you like to join the PKI Consortium? Go to pkic.org/join, or contact us if you would like to become a sponsor.
That we have you here. This is the mic. Please talk closely in the mic. So Scott Aaronson is the Schulberg Phyllis of the University of Texas at Austin. And if I remember correctly, you have been at OpenAI for a while?
I was, yeah, for 2 years.
Okay, so you're now back here at the university?
Yes.
Well, it's great to have you during this conference. Your input, I'm really curious. The discussions you've seen and the talks that we've had is like quantum. For me, like I'm not a cryptographer. I'm in the IT. I know about PKI and I understand more than most people do. But like the way you're thinking about this, and your insights on the reality of quantum computing in general. Let's have the cryptography on the side, which is really important, but it's only important if we actually have a relevant quantum computer. So with that, welcome to Scott Aaronson. We're glad to have him here. He will start the first session of today. Welcome.
Thanks. Is this on? Yeah, sure. Let me take that one. All right, well, thank you so much for inviting me here. This will not be a technical talk. You see, I don't even have slides. I'm just going to pontificate a little bit about the current situation in quantum computing, as I was asked to do, and then I'll be very happy to take any questions. Okay, so actually just a couple hours ago, I told my 7-year-old son that I was headed to give a talk at a conference that was about new encryption codes that would be hard to break even using a quantum computer. So my 7-year-old just looked at me and he said, okay, but if they have a conference about it, then the bad guys will also find out about those codes and they'll use them. And then even if the good guys build a quantum computer, they won't be able to read the bad guys' messages, so they won't have an advantage. So maybe they shouldn't have that conference. But I think this actually raises a relevant point, which is that the basic facts about post-quantum encryption, encryption based on lattices or LWE or other quantum-resistant primitives, are well known to the relevant communities by this point. After like 30 years of thinking about these things. NIST has already held its competition from roughly 2017 until 2022 to agree on standards for post-quantum cryptography, where some proposals were actually broken, and the community seems to have coalesced around the lattice and LWE based schemes, and the process of migrating to post-quantum cryptography has already begun. And you're going to hear a lot more about that in this conference from people who are much, much more knowledgeable about that process than I am. Of course, we don't know for certain if these systems are actually secure against quantum computers or against classical computers, for that matter. Just like we don't know for certain if RSA or Diffie-Hellman or elliptic curve cryptography are secure against classical computers. Unconditional proof is hard to come by in computational complexity. Okay, but I'm not a cryptographer or a number theorist, and unfortunately, I don't have all that much to add to that conversation. Usually, when I talk to people who are working on post-quantum cryptography, the main thing that they want to know from me is some variant of, how much time do we got, Doc? So in other words, how long until someone builds a scalable, fault-tolerant quantum computer that is capable of running Shor's algorithm at a large scale? Well, Unfortunately, I don't know the answer to that one either. I like to say that, if I could predict how long different technologies would take to come to fruition, I wouldn't be a professor. I would be an investor, right? But maybe I can at least offer some perspectives that are helpful for thinking about that question. So, a kind introduction just mentioned that I'm coming back to quantum computing from a 2-year leave at OpenAI, thinking about AI safety. By the way, the safety group at OpenAI no longer exists, unfortunately. But let's consider AI as a test case. Like say conversational AI that can write code, solve math competition problems. When I was a student in the 1990s, there were all these sane, reasonable people saying, well, look, every decade we're promised the AI, like the kind from Star Trek, is just around the corner. Every decade, it yet again fails to materialize. So our guess should be, there is zero real progress here. This thing is just indefinitely far off, unless and until there is some conceptual breakthrough on the true nature of intelligence. And then there were the crazy nutcases who were saying, no, you just have to look at trend lines and extrapolate. Moore's law means that the number of flops per second that you can do is doubling every couple of years. And if you just plot that on a log plot, then you'll see that we're going to be able to have neural nets roughly as large as the human brain by sometime in the 2020s. Okay, and so our prediction should be, AI that will transform civilization sometime in the 2020s. Okay, now the amazing thing is that we've now run the experiment, and we learned that the nutcases were right. So it really was just a matter of following trend lines, all the way to a science fiction sounding conclusion. And there are a few people like, Gary Marcus, I think are still skeptical, maybe, in denial about what has happened. But, to be a skeptic these days, you have to keep moving the goalposts to a sort of, crazy extent. From, a few years ago, GPT-3 can't even do elementary school arithmetic, haha, look at that, to today, the O3 model can't yet solve all the problems in the International Math Olympiad. Okay, so what happens if we apply that same methodology of just naively looking at trend lines to quantum computing? Well, first of all, the relevant metric is not the number of qubits. I don't care how many qubits someone has if they're crap. Okay, the relevant metric is how accurately can you apply, let's say, a 2-qubit gate. Okay, so we've understood since the mid-1990s that if you could get the error per 2-qubit gate down below some constant threshold, then the theory of quantum fault tolerance can get you the rest of the way, okay, to a device with thousands of encoded logical qubits, which could mean millions of physical qubits, billions of physical gates, running, say, Shor's algorithm to break 2048-bit RSA. Okay, so the trouble in the 1990s was just that the achievable error rates were ridiculously far from that threshold, right? It would have been amazing back then to do a 2-qubit gate with 50% accuracy. Okay, but what has happened in the 30 years since then? Well, at some point that 50% became 90%. Okay, and then the 90% became 99%. Okay, with Google's 53-qubit quantum supremacy experiment that they did in 2019, they had 99.5% 2-qubit gates. Okay, now with the results that we've seen announced just this past year from Google and Quantinuum in Colorado and Quera in Boston and others, we're now very near 2-qubit gates with 99.9% fidelity. Okay, and 99.9% is already past some estimates for the fault tolerance threshold. Okay, of course it would be nice to go even further. Okay, but already a month ago, as you may have seen, Google announced this 103-qubit superconducting chip that they built called Willow, where they used a quantum error correcting code called the surface code, okay, to protect a single logical qubit. Okay, so we're just talking about one error-corrected qubit right now. Okay, but for the first time, they are well past the threshold where, as they use more and more physical qubits to, so they use a bigger and bigger code, the encoded logical qubit is staying alive for longer and longer. Okay, so and so far everything is working exactly like the theory of quantum error correction said it would work in the 1990s. Okay, so there are still skeptics of quantum computing, like the mathematician Gil Kalai, right? But they have made clear predictions that at least I took to imply that you would not be able to get to this point. That there would be some sort of correlated noise acting on your physical qubits that would violate the assumptions of quantum error correction. Okay, we've seen no signs of that correlated noise. So of course the skeptics haven't conceded anything. Okay, but to my mind, to the extent that they made a clear physical prediction, it's now been tested, and the results are not consistent with that. Okay, they're consistent with what you could call the boring conservative possibility that quantum computing should work, just like the theory said. Okay, so I want to be clear. A single logical qubit is still a hell of a long way from Shor's algorithm breaking RSA 2048, let's say. For the latter, you would want millions of physical qubits, right, like thousands of physical qubits per logical qubit, probably. And those might then need to be spread across thousands of dilution refrigerators, if these are superconducting qubits, or thousands of magnetic traps, if these are trapped ion qubits. So now you're talking about filling a whole building with these dilution fridges or with these traps, using lots of electricity. No one possibly spending days or a week to do your factoring. Certainly no one has ever built a quantum system at that kind of scale before. But I would say that we're now roughly in the same situation as for a nuclear bomb in 1942. In other words, it is now mostly a question of how badly do people want this and how much are they willing to spend. Okay, so thankfully, we don't currently have a world war that is accelerating the timelines. Okay, but Google, IBM, Microsoft, Amazon, Quantinuum, Quera, PsiQuantum, the Chinese government, and many other actors are now collectively spending, depending on how you count, probably tens of billions of dollars per year on quantum information research. Okay, so whether it's wise or it's unwise, that is happening. Okay, so what is the skeptical case at this point? Well, you can say maybe people will lose interest, they'll run out of funding, they'll get distracted by AI. AI will take over the world, and this won't be relevant. And then, of course, there are still people who say, well, maybe quantum mechanics itself will break down at the relevant scale, okay? Or maybe it won't work the way that we thought it did, okay? And in some sense, I hope that that's true, right? That would be a revolution in physics, as opposed to a mere success in building a quantum computer, which would just confirm what we thought all along. But in any case, you definitely don't want to rest the security of your encryption on the hope of quantum mechanics being wrong. Okay. So, and then I think, often there's just this intuition when I talk to people that quantum computing just sounds too good to be true. It sounds too much like science fiction. There must be a catch. Okay, but often when I try to probe that further, what I find is that, they have these sort of standard misconceptions about what a quantum computer is or would be good for that you would get from reading the popular articles about it, right? They think that a quantum computer would just magically try every possible solution in parallel and then pick the best one, okay? In which case, it would not merely break RSA or Diffie-Hellman, it would break symmetric key cryptography as well. In fact, it would solve NP-complete problems in polynomial time, and it would do so much more than that. Okay, but I probably don't need to tell most of you that that's not how a quantum computer works. It's much more subtle than that. Okay, you need to use interference among amplitudes to sort of boost the amplitude of the answer that you want, while getting the contributions to the amplitudes of the wrong answers to cancel each other out, to destructively interfere with each other. Okay, it is mostly just for a few special problems that we really know how to do that in a way that would get an exponential speed up over the best known classical algorithm. Okay, it just so happens that those problems include factoring, discrete logs, elliptic curve problems, and other things that we base the security of the modern internet on. Okay, so, but once you explain the sort of weird pattern of capabilities and limitations that quantum computers would have, that they do promise exponential speedups for these few very special problems, but for other problems like optimization problems or combinatorial search or machine learning, we mostly just hope for the much more modest kind of quadratic type speed up that you could get from Grover's algorithm. Once you explain that, then they say, yeah, I guess that is weirder than any science fiction writer would have had the imagination to invent. Okay, and maybe that's not too good to be true. So in summary, I would say that if someone has secrets that they really need to stay secret for another decade, then I would strongly advise them to already worry about quantum computing. That doesn't mean that I know that you will have this in the next decade. That just means that I don't know that you won't. Okay, so let me just address one last question, which is, you might say, well, if the main impact that quantum computing will have in the world is just to break existing public key cryptography, and then, that will create this, enormous headache for all of you folks, and the whole world will then need to migrate to post-quantum encryption. But once that happens, we'll all just kind of be back where we started. Then you might say, well, then what's the point? Why should we even bother to build scalable quantum computers? And well, one answer, of course, is that it's hard for any one person to decide that unilaterally, right? The fact that you decide not to build it doesn't mean that everyone else will including adversaries, will make the same decision. Okay, but another answer, of course, is that that's not the only application of a quantum computer. Beyond breaking public key cryptography, there remains the original application that Richard Feynman and others were talking about in the early 1980s, and that's simulating quantum mechanics itself. Okay, and that will hopefully have enormous beneficial uses in designing new materials, understanding high temperature superconductivity, maybe building better photovoltaics, things like that. And hopefully we'll be able to realize some of those applications even before we have a fully scalable fault-tolerant device. So I would expect some of those applications to come sooner than breaking of RSA 2048. Okay, but I like to say that for me personally, the #1 application of a quantum computer has always been not breaking public key cryptography, not even simulating quantum physics and chemistry, but simply disproving the people who said that quantum computing was impossible. Okay, for me, it would be worth it just for that application. And so I'm very glad that post-quantum encryption exists to mitigate some of the downsides of satisfying our curiosity about this matter. And at this point, I'm very happy to take any questions.
Yeah. Okay. Okay. So thank you. And yeah, indeed, come up to the mic. There's a mic here in the middle. We will try to take questions from, let's start with one in the room. Then I will ask Albert if there are any questions from remote attendees, so they have an equal opportunity to ask the question. Well, thank you.
Hey, Scott.
Hey.
Will Oxford Nanometric. I'm one of those crazy people that predict that we don't have as much time as we think we do. And I think I can base that on two observations. One is that if you look at the history of regular computing, there was this group in the English countryside that basically built a computer long before the public was aware.
I've heard of them, yes.
Yes, right. Few people there that you might have recognized. And of course the public did not know about that. It seems clear to me that you could build a Shor's algorithm machine that is not a general quantum computing engine. And in fact, the only part of Shor's algorithm that needs to be run in the quantum is the quantum FFT. So to me, I think that whether we know it or not, there's probably a lot more capability of breaking RSA than we know. So that's my first observation. Second is that it doesn't require incredibly good gate fidelities, because you can test the answer very quickly. And so you can spend 3 years calculating something that you can test in 5 milliseconds. So I think both of those things make me a lot more skeptical that we're actually safe.
Yeah, well, it's certainly important here that factoring is an NP problem, which means that we can go way beyond the scale where a classical computer can simulate it and still know whether we got the right answer or not. That is not a property that is shared, by the way, by the current quantum supremacy experiments, which is a huge issue for those experiments. And, as someone who helped design these experiments, I'm acutely aware of that. Okay, but now to speak to your first observation, obviously, I am not privy to any classified information. Okay, but I think it's very important that it's amazing that both Bletchley Park and the Manhattan Project were able to be kept pretty much secret throughout the Second World War. I mean, that was in a different world where there was wartime censorship, right? I like to joke that if someone tried to start like a secret a Manhattan Project today to build a quantum computer, like within 15 minutes. Like hashtag what's going on in Los Alamos would be trending on Twitter, right? And it's much harder to keep secrets on that scale today. And the other thing is that the quantum computing community is not that huge. We sort of know who the top experimentalists are, and we haven't witnessed them disappearing into a black hole. Right, and so I find that of course I have less visibility into what's happening in China, for example, but that I find hard to square with the existence of some giant secret effort.
Okay, so thank you, Albert. Do we have any questions from the remote audience?
Yeah, we have a question from James, and he's asking Scott, what about your thoughts of collecting now attack later methodology concerning quantum computers and the potential preventative measures or solutions?
Sorry, I didn't understand the question. Could you say it again?
I can
maybe?
say it again. What are your thoughts about the collect now, attack later methodology?
Oh, yes. Well, I mean, almost certainly people are doing that. It would be shocking if they weren't. If the relevant intelligence agencies were not storing, vast amounts of encrypted data in the hopes that they will later be able to decrypt it using a quantum computer or using whatever else. And that is a central reason why I said in my talk that if you have secrets that need to be kept secret for another decade, then you ought to already be worrying about this. Yes.
Okay, let's take the next question from the room.
Yes. Hello. Thank you, for Professor Aaronson. Yeah. My question is about the dilution, the cubic technologies which require ultra cold, in other words, dilution refrigeration. You mentioned thousands of dilution refrigerators. Doesn't dilution refrigerators require helium-3, and don't we have a limited supply of that? Isn't that a limiting factor for that technology?
Yeah, I mean, you should find an experimentalist who could speak to that more. I mean, I don't I don't know if they all require helium-3 or if there are alternate paths to it. But in any case, I expect that while the world does have only a limited amount of helium, it probably has enough to run a device like this.
What we have is mostly helium-4. Helium-3 is very rare.
So I can't I can't actually speak to that knowledgeably, but I can say that when people find things like this, almost always there is a workaround, right? So I mean, people were saying for years that well maybe cosmic rays hitting your chip are going to rule out superconducting quantum computing scaling. Okay, that problem has now mostly been solved, right?
Or maybe a workaround is a qubit technology which does not require dilution refrigeration, like trapped ion.
That's right. So that would be a good question for an experimentalist. Yes.
Okay, thank you. So Albert, do we have more questions from remote?
Yeah, there's another one. No name, but he's asking, humanity is adept at solving manufacturing problems. What is a current estimate for when the creation of qubits and relevant gate logic becomes a manufacturing problem?
I mean, to some extent, it is already a manufacturing problem, right? I mean, the main source of progress that there's been, on building systems with, that integrate large numbers of qubits and gates, over the last 10 years or even 20 years, it hasn't been any theoretical breakthrough, right? I mean, and as a theorist, it pains me a little bit to say this. I wish that we could take more credit, but, the main, relevant, theoretical ideas for this discussion were already in place in the 1990s, right? And the progress that has gotten us to where we are now has mostly been in manufacturing. In fabricating chips that can, support Josephson junction, superconducting qubits that just act more and more accurately. A lot of very careful engineering to understand the sources of noise and decoherence and just sort of tamp down on them one by one.
Okay, so let's take the next question from the room.
Yes, my question is related to the the accuracy of a single or 2 qubit circuit. You have been speaking about 99.9 and 99.99, but my question is, did you take into account readout error? Because with readout error, my numbers, I mean, numbers that I have are lower.
Yeah, so certainly the people who do these experiments take into account readout error. That's not usually the limiting source of error, right? So there is some error in the readout, as there's some error in the initial state preparation and everything else. But most of your gates that you're applying are somewhere in the middle, right? So just quantitatively, that's the bulk of the possible places where an error could happen. But yeah, certainly when you actually do these experiments, you do have to worry about readout error. I think that the readout error, might be, on the order of, I don't know what it is, 1%, 2%. Even if then, each qubit is only being measured once, right? So, yeah.
Okay. So just a reminder, if you want to ask any questions, come up to the mic here. For remote questions, go to pkic.org/ask, where we collect all these questions. We will try to answer them all. We're almost at the end of the talk. But Albert, do we have any more questions from remote?
Yeah, there's also a talk to you, Paul.
To me?
Yeah, to you. Is there a way to share the streaming link for in-person attendees? It would be nice to screenshot slides, for example.
Yeah, no, absolutely. Also, we do have recordings of all the slides, so you don't have to screenshot them now. You can do that later. We also make all the slides available on the website, so as soon as the conference is over, you can download the PDF files, like we did with prior conferences. Well, it would be maybe take a week or two before we're ready with that, but you will be able to download them there. But this morning, you should have all received an email with a link to the live stream. If you cannot find that, just go to the website, click on the PKIC, the conference site, and then type at the end of the URL live stream. Then you always go to the live stream as well. So I hope that answers the question. We have another question from the room.
Yes, my name is James. I'm with the street team of Curel. I was wondering, what do you think about the coupling of AI and quantum computers? Possibly when AI becomes more advanced, could quantum computers be programmed by AI rather than human and then eliminate some of that error?
Yeah, so I mean, the main sources of error that I've been talking about have just been like decoherence caused by coupling to the environment. Okay, but already you can see AI affecting this as it is as a special case of AI affecting everything in the entire world that humans do, right? But there are papers already that use neural nets to do the identification of the error syndrome. After you make the intermediate measurements in a quantum circuit, and they actually get better results than you got from non-neural net based methods, right? So we already see AI sort of being applied at that level in quantum error correction. I expect that that would very likely just become a standard way of doing error syndrome identification. And more generally, I'm sure that people will be using AI for optimizing the sizes of quantum circuits, doing things like that. The bigger fear I think that people in quantum computing have is that of the positive uses of a quantum computer, like for quantum simulation, for simulating protein folding as an example, simulating dynamics of many body quantum systems. Many of those can now be done using classical AI. Just much better than they could be done a few years ago, right? Using AlphaFold, for example, okay? And so to some extent that competes with quantum computing. That if that becomes too good, then that removes a lot of the positive case for building a quantum computer, okay? But hopefully, the combination of AI with a quantum computer will be able to stay ahead of AI without a quantum computer, at least for some special tasks.
Okay,
Thank you.
So we have 1 minute left. Let's take one question from the remote. Try to answer it quickly. Albert, I see we have a lot of questions coming in, so pick one.
Yeah, I have a nice one. If most critical targets have moved to PQC algorithms by the time a quantum computer is able to solve most useful use cases, who is going to pay billions to build a quantum resilient CRQC?
Yeah. Well, so I don't know, but I can say that the money that is now being invested in quantum computing, the vast majority of it, is not actually motivated by breaking public key cryptography. Okay, it is motivated by the hope that quantum computing is going to revolutionize, machine learning and AI and finance and all of these other application areas. Now, some of those hopes I view as wildly exaggerated, and based on not actually rooted in the quantum algorithms that we know. Okay, but be that as it may, if you talk to the people who are funding these efforts, right, it's not about breaking public key crypto. It's about achieving these various positive uses. And of those, I would say quantum simulation is certainly a serious one.
Okay, well, thank you, Scott Aaronson. Have a big applause.